What? Uh, so, how's your midterm? Good. Maybe next week we will finish and we'll give the score. I hope this weekend I can finish and I can give you next week. Okay. So today I would like to have a little bit review on chapter 12, the factors. I hope you are able to view the additional content that is about factors. Okay, so I think we can start with some example. Okay, we have these three questions. Okay. So this is questions about vectors. Finding the parametric equations and symmetric equation. I hope you know these two. So parametric equation is equation that you can bring that equaling all the axes, okay, with the terms of t. Okay. And symmetric equation is when you are going to equaling this t, equaling into the h, x, y, z. So the point is, you see three type of questions. First question is you go point and point. Okay. So I think you can imagine what's directions, right? The first one, you can get the direction easily from the points, right? But the second question or the third question, it has some property that is, the second one is perpendicular to some other vectors, right? So you can get the direction also from this perpendicular to both of this and this. And the third one is the intersections. Okay? So intersections means that you have a plane this first plane, and then you have the second plane. And it's asking the intersection between these two planes. Okay. Okay. So I think I will give you some steps how to see this. How to see this through. So first is I will write here, need to know the direction, right? Or in this case, this is what we call the vector v. Usually we name this as a vector v. Okay? So for the first one, we can take the vector v . 1 minus 5, 6 minus 2, minus 2 minus 5. And this will be 6, 4, negative 7. We can take this as our directions. Okay. Which means that this direction is parallel to our line. Okay. To our line is parallel. And then based on this vector, our initial positions is, let's say, the negative 5, 2, 5. Okay. This means initial. Initial point. So based on this, what parametric means is, so let me write parametric equations then. For x, we start from the initial point, negative 5, plus the element from vector v, so plus 6d. Okay, and then y is 2 plus 4d. Okay, and z is 5 negative 7d. Okay. And symmetric equations, we can rewrite this x and y and z, all these terms, with t. So we can write t is x plus 5 over 6, right? And here we can also write t is y minus 2 over 4. And here t is z minus 5 over 7, but it's negative. Let's say negative like that. So the symmetric equation from this t, we can just equaling all of them. So x plus 5 over 6 equal y minus 2 over 4 equal z minus 5 over negative 7. Okay, that's what the definitions, okay, the parametric and symmetric. Okay. Okay, I hope from this example, I think it should be clear what should you do to find the parametric and the symmetric. Okay. So the first thing is need to know the directions. Okay, need to know the directions. And the second one, we need to find a line that through the point 2, 1, 0, and then those line is perpendicular. Okay. Is perpendicular to both vectors I plus j and j plus k. So which means that, imagine that this I plus j and j plus k is just perhaps I plus j is maybe on the x and y, right? And j plus k is on the y and z, so maybe here. So we need to find one vector that is perpendicular to both of this, right? Maybe this is not really clear. So let's say we have this two lines like this, okay? And we need to find another line that is going through here, right? That is perpendicular to both of this and this, okay? Which means that we need to take the cross product, okay? We need to take the cross product to make sure that we get the line that is perpendicular to both of these vectors, okay? So this perpendicular can be solved through the cross product, okay? The cross product. So the second question, finding cross product. This is perpendicular to both vectors. So we take the cross product. So I plus j cross j plus k, and let's make this as our v. Okay? So this is our directions, right? So we can take I, j, k, 1, 1, 0, and 0, 1, 1, right? And I'm usually adding this I and j again and write this. This is my typical way to check. So this will be wait. Let me make it clear. Should be from here. So that will be I plus k minus j. Okay, or I minus j plus k. Okay. This is our vectors, which means we can write vector v, 1, -1, and 1. So parametric. So if we take p0, the initial point as 2, 1, 0, then parametric will be x is 2 plus t, y is 1 minus t, and z will be t. Now similarly, we can take the symmetric equations and write as x minus 2 equal 1 minus y equal z. This is symmetric equations. Okay, now the third one is asking the same questions, but this is now we have intersection of the plane. Okay, but let me write in the new page. So intersections. So intersections of planes x plus 2. Okay. Now, if we look at these two equations, we have this and this. Okay. First is maybe make sure that this is going to be an intersection between those planes. How do we know? We can check with some points. The easiest point maybe 1 and 0. I think if you see how the arrangement of the x, y, and z, we can see that when we take 1, 0, 0, we see that it is going to be the same, right? It's going to be the same. So we can know that the two planes are maybe have an intersection. Okay, and we can also take this 1, 0, 0 as our p0 or the initial point. Now we need to know the directions. Again, the process is we need to find which way this vector is headed. Okay, so still we need to find directions. So imagine that we have two planes like this, and perhaps this is also the planes, and it's intersected at that point. Okay, the best way to see this two planes, we need some directions that is, or we need one line that is perpendicular to these two planes, which means that maybe if we take this as our line in the plane, then we need to take whether we need to have another line that is perpendicular to these planes, right? So we need to find directions. So find a line that is perpendicular to normal vectors of planes. Let's say normal vector is going here, right? One side, and another one is going here. So we need to find this line here, and that is perpendicular to both normal. So this n1 and n2, right? So basically, this is also a cross product, right? So the vector v, the direction that we want, is cross product between these two. Okay. And n1, we can write 1, 2, 3. N2 is 1, -1, and 1, right? Okay, and then let's take the cross product. So v is one, 2, 3, 1, -1, 1. Oh, I think I will directly compute this. So I, j, 1, 2, 1, -1. So this will be 2i plus 3j minus k minus 2k minus 3i plus j. So this is 5i plus 2j minus 3k, or we can write the factor b is 5, 2, and negative 3, right? Okay. So we get v, and then we assume the initial point is 1, 0, 0, because that at that point we get the first intersections, right? So we get the parametric is initial point plus the direction b. So x is 1 plus 5t, y is 2t, and z is negative 3t. And symmetric is x minus 1 over 5 for the x part, and then this will be y over 2, and this will be z over negative 3. And that's how we get it. Okay. Okay, that's about the parametric equation for the line. Okay. And another question that I would like to review is the plane, okay? The equation of the plane. Let me write on the bottom here some questions, maybe just 2 questions probably. So find an equation of the plane through point 5, negative 2, 4, perpendicular to vector negative I plus 2j plus 3k. I think just one question, I think should be enough. And the other questions not necessarily. Okay, I think just one, I think it should be enough. Okay, the next question is finding equation of the plane. So we have a point 5, negative 2, and 4, and we have a vectors negative 1, I plus 2j plus 3k. So the plane should be perpendicular to this vector. So we can say, if we take, like, for example, we take just a random plane just to visualize this. This plane should have the normal vector, right? In the plane. And then we have a vector that is perpendicular to the plane, which is, they are the same direction to our normal vectors of the plane, right? So we can treat these vectors as our normal. Okay, so we can take this as our n. So we can take so usually n we take with terms a, b, c in this case, and in our case this is negative 1, 2, and 3. Okay, and then setting the initial point, which is we take x0, y0, z0. Or maybe let me write directly. So x0 is 5, y0 is -2, z0 is 4. So the equation of a plane is A x minus x0 plus b y minus y0 plus c z minus z0 equals 0. Okay. So we get negative x minus 5 plus 2 y plus 2 plus 3 z minus 4 equals 0. And if we solve this, negative x plus 2y plus 3z 5 plus 4 is 9. 9 minus 12 is minus 3, so it's equal 3. Okay, that's a little bit review on line and plane in vectors. The rest I think I can give as an exercise, and also maybe you can have more practice with your TA. So my goal this week, finishing these factors, and maybe tomorrow we could have a new chapter 13, and I think tomorrow we can finish all the necessary sections for chapter 13. Okay. Chapter 13 is really short. So it's about the calculus, but in vectors. Okay, in vectors. So all the calculus part, it's the same, but we deal with vectors. Okay, so we just add some additional points. And next week we move to chapter 14. So 14, 15. In that will be the last part of our lecture, and after that final exam. So as far as I observe in our schedule, so far we're still in probably the first week of June exam, the final. And I think still in line with the schedule, unless there will be something happen when we deal with chapter 14 or 15. But I hope still the same, so you can have more time if you have other exam as well. Okay, so let's move to one more section, which we call the cylinders and the quadric. So cylinders and a quadric surface. So in 3 dimension, if we would like to write, for example, we have the z equal x squared. Okay. So we start by, if we take this into 3 dimension, let's say this is z, this is x, this is y. If we think only in 2 dimensions, the z and x can be dealt as usual. So z equal x squared means that this goes like that, right? But then there are no mentioning y, right? The y-axis. So which means that in every point of y, this z equal x squared will be also applied. So we could have that, that, and that. So if we take all together, then we are getting this image. Okay, this is what we call the parabolic cylinder. Okay, so this is parabolic cylinder. So it makes a cylinder. So cylinder is all lines that is keeping together and making a new shape. Okay, and then yeah, we can say that in that way. The same way, if we take, for example, if we take x squared plus y squared equal 1, we know that in 2 dimensions this will be a circle. But if we include z, so let's say this is the x, y, and z. So we know that in 2 dimensions it will be a circle. So let me draw a circle here. But then in z, it's also applied at every point of z. So we are going to have that, and then we are making like a cylinder, like a cylinder in geometric perspective. Okay, so we have this, okay, and we have also, if we take it into y squared and plus z squared equal 1, it's the same but in different axes. And perhaps I will write the general equations for this quadric surfaces. So this will be ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus gx plus hy plus iz plus j. Okay, really long. But this is for general equation, so all possible combinations should be written down. But in our case, it depends. Okay, it depends. Some constant can be 0 in some cases. So this is general equation for quadric surface. So as the name suggests, quadric means from the quadratic, means that you will have at most, it has a square. It has a square in the variable. Okay, and then it is a surface. So which means that this is going to be taking shape like the first section here. Okay, so we are going to see some combinations. Okay? So if you have learned before the conic sections, we have the ellipse, we have the parabola, we have the hyperbola. Okay? Now we are going to combine all together. Okay? So we have some combination of those conics. So we can combine parabola with an ellipse. So imagine you have a parabola, but then you have an ellipse here that is limiting the upper side or downside of the parabola, and you will have a new shape, And we are going to identify all those shapes within these sections. Okay, to get through the all the shapes in the surface, let me go through for example on how we trace the shapes. Okay. Let's say we start from x squared plus y squared over 9 plus z squared over 4 equal 1. Okay. Now, how do we identify this? Okay. The best way to identify is taking some part of variable with 0. So exchange, for example, exchange z equals 0. Okay, let's assume that z is 0. So we get x squared plus y squared over 9 equal 1. And we know that this is an ellipse, right? It's an ellipse, right? This is an ellipse. So we have an ellipse for xy. So basically we can try to okay. So this will be z xy. Okay, so x, this is only 1, right? The distance. For y, it's 3, right? If you remember the conic section, so let me draw. This is 3, this is -3, this is 1, -1. So the ellipse is going to be here, right? Okay. But the total, we have z, right? So we can make another assumption that makes y equal 0. So we will get x squared plus z squared over 4 equal 1. Now this is another ellipse, right? This is another ellipse. So x and z, so x is 1 and z is 2, the distance, right? Distance in ellipse. Let me write with the green color. So 2 is maybe here and maybe down here. So this will be our ellipse. Okay? So we will have both here and both here. And if we imagine, let's say this part, okay, let's say we take z with some constant, then this will move. If this is going to be positive side, this goes up on the upper side. If we take z as a negative, we go downside, right? And it will be limited from here, and we can see when we trace all the possible lines, we are getting this shape. Like a rugby, American football, right? We call this an ellipsoid. Okay, we call this ellipsoid. So the form is x squared, y squared, z squared, and if they are the ellipse, we call it ellipsoid. If 9 and 4, let's say it's becoming 1. So x squared plus y squared, z squared is become a sphere. Okay. It's become a circle. Right? Okay. So your goal within the sections is to identify. How to identify? Taking some part with 0. Okay, taking some part with 0. And you will see some patterns. You will see some patterns at the end. Okay, next one. Okay, yeah, this is the ellipsoid. Okay. And then another example is z 4x squared plus y squared. Okay. Again, to identify, we can take some variable as 0. So let's say we take the x, then we have z equal y squared, right? And we can take y equals 0, and z is 4x squared. So we have a parabola, right? Parabola for zy plane and zx plane, right? And of course, if we take the z as a constant, let's say take 1, right? So we have 1, or let's say if this is let's say 4. So 4x squared plus y squared equal 4, and x squared plus y squared over 4 is equal 1. So we have an ellipse at z equal 4. So at z equal 4, at that point, we have a plane that is going to be an ellipse. So this will be parabola. This will be an ellipse. So we call this elliptic paraboloid. So you have a parabola, and at the end you will have an ellipse to close down the parabola. So let me go through this picture here. Okay, that is the picture. Okay, I think I don't need to trace. think we can have a break. Right? Okay, so let's go for the next one here. So another example. Z equal y squared minus x squared. Now this is one of the, I think, a difficult shape to be drawn. This is called the hyperbolic paraboloid. So it has an hyperbola and it has a parabola, right? So if we take this and taking, let's say we're taking some constant. Okay. So let's say we start from z. Let's say z equal a constant, any constant. So we will have y squared minus x squared, right? And we can imagine k can be 1 or -1. Okay, the constant can be 1, -1, because if we do that way, we can have y squared minus x squared or x squared minus y squared. So we can have both. So let's imagine, let's assume that this would be -1 and 1. So we can have just a normal like this is a hyperbola, or it's equal -1, which is we are getting x squared minus y squared equal 1, right? Okay. So we can have both sides. Okay, we can have both hyperbola. So that's the first one. The second one that we can trace is, let's take x into k, or we can take the first the x equals 0, and we get z equal y squared. Okay, and y equals 0, and we get z equal -x squared, right? So we are going to see one parabola will be this sides and the other one will be this sides, right? And then imagine that this will be not 0 but constant. So we are going to see in every point that this parabola will take place. Okay. So if we could take for example, for z equal y squared minus k squared. Okay, let's say this. If x is a constant k, then we will have this equations. So we can start looking at this, and maybe taking this 3 dimensions space. Okay, and then z equal y squared, we start from the middle here. That's when k is 0. Okay, that's the parabola when k equals 0. And then k, because it's k squared, k can be 1 and -1, right? It can be positive or negative, right? Let's say we take the -1. Let's say we can take the k -1 and 1, right? So we can have at this side -1 and 1. So we can have y squared -1, right? -1. So we are going to take, or we are going to move the graph downside 1 unit, right? So at -1 here, we are going to take this downside and this downside. But of course, in between the 0 and 1, we can also have a parabola, right? So it's kind of taking, okay. So you can see that this will connect all the points. Okay, and then we take the other parabola. So let's make y as a constant and take z equal k squared minus x squared. Now we can have the another side of parabola for zx plane. Let's use red color, blue color. So z equal to negative x squared will be going to be here. Okay, let's say that's our z equal negative x squared. Okay, and then we can take the k as negative 1 and 1 just to make sure that we see the patterns. So 1 is maybe here and negative 1 is here, and we are going to see it's moving through this size here upside 1 point, right? And then you'll see we can also connect this vertex, the vertex we can connect all. Okay. Now the last part is the hyperbola. The hyperbola, we can write y squared minus x squared as equal k, and k we can take it plus 1 and negative 1, right? So we can have y squared minus x squared equal 1, or x squared minus y squared equal 1. And if we take that into graphs, now we can take z as k, right? And we can take that as a 1 and negative 1. And we are going to focus on xy plane. Okay. So at this point, z equal 1, we can see that it's going to be y squared minus x squared equal 1, which is going to be this way. If you look from the top side, this is y, this is x. This is going to be this way, okay? You could relate this to the conic sections, the hyperbola, okay? And then when z equal -1, it goes through here. Okay. Okay. And in our picture, if we see from the top side, it will be that way. So now we need to connect all this thing. So the hyperbola will be at the end of the sides here, okay? And this will be connecting, so this will be the top side here, and then this will be the outside like that. So it will be, if we connect this two, okay, so this will be, okay, this picture here. Hope this help. Okay. So we connect all these three shapes, the 2 parabola and 1 hyperbola, or we can say 2 hyperbola. We can have within 2 motions, and this is what we have. Okay. So we can have this parabola here, and also parabola outside here. Okay. And it's going to be limited by the hyperbola here and hyperbola here. Okay. Or in another picture, we can also draw like this, which is very similar to a saddle if you ride a horse. And the point that is on the middle here at the origin, we call this a saddle point. Okay. Please keep in mind, we are going to see the saddle point in the chapter 14, okay, when we deal with the partial derivative. We are going to be able to compute the saddle point. I mean, how to determine the points on that saddle point. So this is, the name is hyperbolic paraboloid. Okay, another example. Is this example. So we can take y equals 0. And we can write x squared over 4 plus or minus now a hyperbola, right? And then we can take the x equals 0. Another hyperbola. And then when z equals 0, we get an ellipse. So this is hyperbola, and we have an ellipse. So if we take times and draw the possible outcome, so we have the xy here. So at z equals 0 means that at the origin, at the origin plane, this will be, we have 2, maybe here, this is 2, -2, this is 1. So we have an ellipse over there, right? But then we have hyperbola on xz and yz. So yz, we have y squared minus z squared. Okay, y squared minus z squared, it should be going over here. That's the hyperbola. And then x and z is going to be this way. It should be, they are aligning like one line like that. Yeah, perhaps not really good proportions, but it should be like this. Let me directly draw this part here. Okay, so we have this side here and another part here and this side. Okay, now we call this hyperboloid of one sheet. In other terms, if we have two sheets, okay, a hyperboloid of two sheets. This one here is for the hyperboloid of two sheets. Okay. Okay, to know the difference between all of the possible quadric surface, let me give you a table that we have here. Okay. So we have at least 6 types. The ellipsoid, the cone supposed to be easy to follow. I didn't mention in the example. An elliptic paraboloid, hyperbolic paraboloid, and a hyperboloid. Okay. It can be 1 sheet or 2 sheet. Okay. So the best way to look at this 6 example is to look at the equations. Right? So if all variables positive, they are equaling a constant, there will be an ellipsoid. Okay? If A, B, C equal, then it will be a sphere. Okay? And then if we look at the elliptic paraboloid, we see that Z equaling positive x squared plus y squared. Okay? So this will be elliptic paraboloid. And if the positive change to negative, then we have the hyperbolic paraboloid. Okay? And you need to also remember we can exchange x, y, and z. Okay, we can exchange x, y, and z. This is the default one, but you can exchange x to here, and this will be z squared minus y squared. It can be. The difference is we can rotate this. Okay, we can rotate this one that way. Okay. So that's also a possibility. And then we have the cone. The cone has a similar property to the elliptic paraboloid. As you can see, in elliptic paraboloid we can have like that, and in the cone we can have 2 sides because we have the squared. Okay, we have the squared here, so we can have 2 sides over like that, and we can have the hyperboloid of 1 sheet and 2 sheet. Okay, the difference is it has a negative on the 1. In the 2 sheets we have negative 2 negative signs here. Okay. I think you can get the pattern for the formula. Okay. But at the end of the day, if you are not really convincing, like maybe you don't really remember the formula, one way to look at the surface is through the trace. Okay, so you need to imagine some part of it, maybe 0, maybe constant, and you need to imagine how it looks like. Okay, I think that's the best way, okay, because but if you want to like memorize all of this, that's okay. At least maybe memorize 1 or 2, and then the rest is you need just to change the signs. Okay, maybe you just change the signs. And the typical questions for this part is maybe to identify the equations, or probably to check whether or maybe trace the sketching. That's probably a typical question for this one. Okay. Not really much of problems. Okay, I mean the variations not really that much. Okay, and then that's finished for the chapter 12. Okay, now after chapter 12, we can move to chapter 13. Okay. So go chapter 13. and then tomorrow we can finish and complete the chapter. Okay, I hope you have taken notes. So chapter 13. This is what we call the vector functions. So let me start with some definitions. What is the vector functions? So vector valued functions. So it is the functions that has a specific property of vectors. Okay? You can say the domain for this functions is all the real number, okay, some set of real numbers, and the range will be a set of vectors. Usually we write the vector valued function with rt like that. And this will be going to be written as ft, gt, ht. Okay. Where the f, g, and h, they are all valued or real functions. So real functions. And t is as in parametric, it's a parameter or independent variable. So we are going to write down the vector using this r, okay, a lot this chapter. And then all these subsections for this chapter 13 will be very similar to what we have in derivatives and integral. So I think we can start with the limit and continuity, which is the same definition as we did, but now we are going to apply it within this R. So if this is our vector function, then we take limit, then we take limit for all the components. And also we need to make sure that provided the limits of components exist. And continue is the same. Okay. So R is, or maybe RT continues at some A if limit the same as its functions at A. Okay, now let me explain a little bit about space curve. So let's say we are having three-dimensional system like this. And then let's say we have like a random curve, and it has the directions. Okay. So let's say this is curve C, and then we have within this system we have a vector functions. So we have RT. Okay. This is going to be FT, GT. Okay. And this is a point P. This is origin. And point P is FT, GT, HT. Okay. Now we can write the point in terms of x is ft, y is gt, and z is ht. Okay. And t will be various, okay, like a parameter. Okay. So through some interval, we can set our value for t. Okay. So the C is, if we call this space curve. So we call this parametric equations, right? Of C, which is the space curve, with parameter t. So we can think the space curve or the curve is we can trace with our vector functions r. So we can trace from t, maybe from t equals something from maybe 0 or negative. So we can take this and then we can evaluate this curve through these vector functions. So we can treat this vector function as our positions, right? Our positions. So we can say that the RT is position vector of P. Okay. quick example on how we at least take the or drawing the curve. Okay, just a quick example. So suppose that we have R that is defined by this equation. So from our parametric, we have x equal cosine t, y equals sine v, and z is equal t, right? Remember that in parametric, we can rewrite cosine and sine, and we can convert them into our Cartesian curve, right? We can write with the help of the polar equations, the x squared plus y squared equal r squared, right? In which we have the cosine squared t plus sine squared t, and this will be equal 1, right? This will be equal 1. And this will be x squared plus y squared equal 1. So we have a circle with the radius 1, okay, for xy plane. But then we have another variable z that is going to be varies with amount of t. So if we take the graph, so let's say this is the circle. Okay. And then we can, so let's imagine that the circle for every t, it will change. So this is a circle. So let's say we are going to move out. So when we change t, we are going to move out the so we are going to have like a helix. So the curve is in helix. Okay. And I think for the other part, we can skip the examples. The next sections is, I think, very similar to calculus. It's the derivatives, integrals, and then later we can also have the arc length as well. And we have another terminology which we call the curvature. Okay, but that part will be, I think, we are going to finish it tomorrow in tomorrow's class. Okay, so I think that's all for today's class. As usual, we are going to have a feedback. No, the feedback, I try to simplify it. So hopefully you can do it. Just have to make sure that you understand the vectors, because I skipped some parts, right, and give you just additional content just to review. So I hope it's enough.